This week, we will examine some more advanced topics in the application of Newton's laws of motion. First, we will look at more examples of constrained motion, where the motion is forced to obey some particular condition in addition to Newton's laws of motion. These conditions usually specify some particular relationship between coordinates of objects in the system we are studying. Specifically, we will re-examine the case of objects suspended with pulleys and ropes, but with more complex systems than we have discussed previously. The fact that the ropes have fixed length will provide a constraint condition relating the coordinates of our various masses. Second, we will examine the case of forces acting on a continuous extended mass distribution, as opposed to acting on discrete point masses. This will allow us to introduce a powerful differential analysis technique from calculus, where we model continuous mass distributions as made up of lots of small, discrete mass elements, and then examine the limiting case of infinitesimally small elements to obtain the continuous behavior. This is a technique that you will see applied over and over again in physics and engineering, and in fact, we will return to it again later in this course. Our specific example will be to study how tension varies in a long, massive rope. This is in contrast to the light, effectively massless ropes that we discussed previously. Finally, we will discuss velocity-dependent forces, that is, forces whose strength depends on the velocity, or some function of the velocity, of the mass being acted on. The most common example of this is resistive forces, or drag forces, which are caused by motion of a solid object through a fluid like air or water. That is the example we will discuss this week. Another example you may be aware of is the magnetic force that acts on a charged particle, which depends upon the velocity of the charged particle. In all three of these cases, we will simply be applying Newton's three laws of motion, but the situations will require a more sophisticated treatment than what has come before.
Let's look at a typical application of Newton's second law for a system of objects. So what I want to consider is a system of pulleys and masses. So I'll have a fixed surface here, a ceiling, and from the ceiling we'll hang a pulley, which I'm going to call pulley A, and this pulley will have a rope attached to it, wrapped around it, and here we have object 1, and the rope goes around the pulley, and now it's going to go around another pulley B, and fixed to the ceiling. So that's fixed. And hanging from pulley B is another mass 2. And our goal in applying Newton's second law is to find the accelerations of objects 1 and 2. Now, how do we approach this? Well, the first thing we have to do is decide, if we're going to apply Newton's second law, what is the system that we'll apply it to? And there's many different ways to choose a system. When we look at this problem, we'll have several different systems. So let's consider the ones that we're going to look at. And the first one is very simple. It will be block 1. And the second system that we look at, we'll call that A. B is pulley A. Now, that brings us to an interesting question about pulley B and block 2. Because we could separately look at pulley B, and we could separately consider block 2, or we consider them together. And I want to first consider separately pulley B and block 2. Now, in some ways, when you're looking at a system of a compound system, and it has 4 objects, it makes sense to apply Newton's second law to each object separately, but we'll pay careful attention to the fact that object 2 is connected to pulley B, and eventually we'll see that we can combine these two things. So the next step is, once we've identified our object, is to draw free body force diagrams for each of the objects. So in order to do that, let's start with object 1. And we want to consider the forces on object 1. Now that brings us to our first issue about what types of assumptions we're making in our system. For instance, we have a rope that's wrapped around this pulley, and we have 2 pulleys that in principle could be rotating. But what we'd like to do to simplify our analysis, So let's keep track of some assumptions here. Our first assumption will be that the mass MP of pulley A and the mass of pulley B are approximately 0. Now, the reason for that is that we're not going to consider any of the fact that these objects have to be put into rotational motion. Later on in the course, we'll see that this will give us a more complicated analysis. We're also going to assume that our rope is not slipping. So the rope is just slipping on the pulleys. So what that means is it's just the rope is sliding as the objects move. Now, again, what this is going to imply is that the tension in the rope, this rope is slipping, and the rope is massless as well. It's very light rope. And all of these assumptions we've seen when we analyzed ropes tell us that the tension T is uniform in the rope. So that's our first assumption. And we need to think about this before we even begin to think about the forces on the object. And now we can draw our forces. What do we have? We have the gravitational force on object 1. And now we can identify the tension pulling in the string, pulling object 1 up. Now, for every time we introduce a free body diagram, recall that we have to choose what we mean by positive directions. And in this case, I'm going to pick a unit vector down, j hat 1 down. So that's my positive direction for force. Now, before I write down all of Newton's laws, I'll just write down our various force diagrams. So for pulley A, I have two strings that are pulling it downwards. So I have tension and tension. And this string, I'm going to call that T2, is holding that pulley up. So we have the force diagram. Now, I could write MAG, but we've assumed that the pulley is massless. And again, I'll call J hat A down. For object 2, let's do pulley B first. Now, what are the forces on pulley B? I have strings on both sides, T. Pulley B is massless, so I'm not putting gravitational force. And I'm pulling, this string is pulling B downwards, so that's T3. And again, we'll write J hat B downwards. And finally, I have block 2. So I'll draw that over here. I'll write block 2. In fact, let's save a little space here. We'll have J hat B downwards. Now, block 2, what do we have there? We have the string pulling up block 2, which we've identified as T3. And we have the gravitational force on block 2 downward, M2G. And there we have J hat 2. So I've now drawn the free body diagrams on the various objects, and that enables me to apply Newton's second law for each of these objects. So let's begin. We'll start with object 1. We have, remember, in all cases, we're going to apply F equals ma. So for object 1, we have m1g positive downward minus t is equal to m1a1. And that's our F equals ma on object 1. So sometimes we'll distinguish that the forces we're getting from our free body diagrams, and A is a mathematical description of the motion. For block 2, we have m2g minus t3 is equal to m2a2. And now for pulley A, we have 2t pointing downwards, minus T2 going upwards. And because pulley A is massless, this is 0. Even though pulley A may be, it's actually fixed too, so it's not even accelerating. And what we see here is this equation. I'm going to quickly note that it tells us that the string holding pulley 2 up, T2, is equal to 2t. Now, so we can think of, if we wanted to know what T2 is, we need to calculate T. And finally, we have B. And what is the forces on B? We have T3 minus 2T. And again, pulley B is 0. And so we see that T3 is equal to 2T. Now, if you think about what I said before about combining systems, if we combine pulley B in block 2, visually what we're doing is we're just adding these two free body diagrams together. When we have a system B and block 2, let's call this J hat downwards. And when we add these free body diagrams together, you see that the T3 is now internal force to the system. It cancels in pair by Newton's second law. And all we have is the two strings going up. So we have T, and we have the gravitational force downward. And separately, when we saw that T3 equals 2T, and we apply it there, then if we consider a system B2, and look at our free body diagram, we have M2G minus 2T, and notice we have the same result there, 2T equals M2A2. So in principle now, and I'll outline our equations, we have equation 1, we have equation 2, and in these two equations, we have three unknowns, T, A1, and A2, but only two equations. And so you might think, what about this missing third equation here? However, in this equation, we have a fourth unknown, T3, and this equation is just relating to T and T3. So in principle, we would have four unknowns in three equations, or if we restrict our attention to these two equations, we have two unknowns, three unknowns, and two equations. Our unknowns are T, A1, and A2. These are our unknowns. And now our next step is to try to figure out what is the missing condition that's relating some of these unknowns. And that will be a constraint condition that we'll analyze next. So when we analyzed Newton's second law applied to this compound system, we had two equations for M1, object 1 and object 2. And what we found is that we had three unknowns, the tension in the string and the accelerations of the two objects. Now, how do we solve this system? Well, we're missing one condition, which is a constraint condition, which is as object 2 moves and object 1 moves, they have to move in some relationship together. And now what we'd like to do is show an analytic approach for finding that constraint condition. And the way we think about it is that we'll call L equal to the length of the string. And this quantity is a constant. And what we'd like to do is introduce coordinate functions for our object 1 and our object 2 and express L in terms of those coordinate functions, and then take two derivatives of L, set that equal to 0 because it's a constant, and that will give us a relationship between the accelerations of objects 1 and 2. Now, this is a little bit tricky, and so what we want to do is very carefully show how we introduce coordinate functions. Recall that we had j hat 1 down and j hat 2 downwards. What that implies is that we're choosing some origin, and let's choose an origin up here. And for a coordinate function for object 1, it has to be consistent with our choice of what we mean by j hat 1. So in this sense, y1 is a positive quantity when we're going downward. Now, what about coordinate functions for the other objects in the system? Well, let's look at a few things first. This is a fixed distance, we'll call it S1, between the center of the pulley and between the ceiling and the center of the pulley. And let's make each of the pulleys a radius r. And let's call this a function yb. And let's make this y2 of t. So now we have coordinate functions for 2 and coordinate functions for 1. And again, recall that this distance here, S2, is a fixed distance. And when we define these coordinate functions in this fashion, we know that the second derivative, d squared y1 dt squared, this is precisely what we mean by the acceleration of object 1. And in the similar fashion, d squared y2 dt squared is what we mean by the acceleration of object 2. So we've introduced a coordinate system. We've made it very clear what we mean by the accelerations of a1 and a2. And now let's look at our constraint condition that the length of the string is constant. So what we're going to do is try to see if we can express the length of this string in terms of all the coordinate functions and some of these ancillary quantities. So what we have here is that the length of the string is yb going down here. So the length of the string has a factor yb. It wraps around pulley B, so that's pi r. And it goes up to this length here. Now, this length is yb minus s1. So that's yb minus s1. We wrap around the pulley again. That's pi r. And now we have this length here, which is y1 minus s1. Now, s1, yeah. And let's just make sure we have all of our quantities here. Now, we also have another constraint condition that this length of the string, we're going to call this L1. We have a second string here, L2. And L2 is given by y2. This length is y2 minus yb. And that was what we called this constant S2. So we now have two string lengths, L2 equals y2 minus yb. And both of these string lengths are constant. And we have the following facts. Let's start with this one first, that the second derivative of L2 dt squared, because the length of the string is a constant, that's 0. And that tells us two derivatives of this is a2, and two derivatives of that is ab. And this is something that we saw before, that block b and 2 are moving together. So when we treated the system as just b and 2 together, we see that the acceleration of 2 and the acceleration of pulley B are the same. So we could have just said that before we began. Now, let's put these equations aside for the moment. And now let's consider taking two derivatives of length of string 1. Recall string 1 is this object here. We'll call this string 1 and this string 2. Now, again, if we take two derivatives, let's look at our expression first. We see that we have two factors of yb, and we have a bunch of constants whose derivative is 0. So we don't have to worry about the wraparound distances, the pi r's. We don't have to worry about the constants s1. All we have to think about is which quantities are changing in time. So we have 2ab when we take two derivatives, and we have one factor of a1, and that's 0. And now, because the block and 2 and pulley B are accelerating together, we have our condition, which is 2a2 plus a1 is 0, or that a1 is equal to minus 2a2. And that is the extra constraint condition that will enable us to solve the system of equations.